Hello everyone, welcome to the Introduction to Mechanical and Industrial Engineering course, MEC 130. This is a new video in the mechanical design. Over the mechanical design subject, we are covering so many topics which are related to the engineering in general, whatever it is, mechanical or industrial engineering in this course. And today over this video, we are going to focus over engineering materials, dynamics, and factor of safety. So what is engineering material or what is material? As we mentioned before that some materials or knowledge in materials and material science and material engineering is one of the fundamental requirements for engineering. We said that engineers, they should have knowledge in mathematics, in material, in addition to other subjects which are related to their major. But material is a core. Whatever your major is, whatever it is, mechanical, industrial, civil engineering, in any way you should have a certain amount of knowledge in this subject. You should know what are the material that you're going to deal with as engineer, and this is what we are going to cover here in this part. We won't gonna go deeply as usual like the other subject. We were not gonna go deeply through this material science or material engineering subject, but I'm just gonna give you an overview about materials. What are the different types of material that we supposed to deal with as engineer? This is gonna be the main objective of this video. All right, so these are the different types of materials that as found in nature or as we are making as engineer. But before we go to these different types of materials, what does it mean a material? Material is something that we can touch, is something that we can use every day. Like for example, if we're gonna talk about your cell phone, it is made of so many different types of material. These materials are different in their chemistry, different in their properties, different in their shape, different in their color, different in lots of things that make this material is totally different than the other material. Like for example, if we're gonna take the cell phone as an example, the cover of the cell phone, it is most likely to be made of a polymer material. Polymer material is one of these materials that we can derive from nature as natural material, like rubber, plastic. These all are different, are classified or grouped as polymers. All right. So, and definitely we're gonna explain what does it mean polymer material. So the cover, it is made of rubber, made of plastic. If we're gonna consider the electronic things inside the cell phone itself, like the board of the cell phone, it is most likely to be made of plastic, and there could be some other material like metals. And if we're gonna talk about the screen of your cell phone, it is already made of glass. In addition to other materials, and definitely will be there. So what does it mean? It means that we do have glass. It is one material type that classified as ceramic. We do have some other metals. We do have some other polymer material that like rubber, plastic, and so on. So these so many material or different material, we are using them together to build a component or something that we every day can use, like the cell phone. You can apply the same concept to anything that you are dealing, like your laptop. The screen or the cover of the laptop is most likely to be made of plastic. But the electronic things inside it, it is made of metal in addition to plastic and other material and other components. The screen itself, it is made of plastic. Some of the screen could be made of a special plastic material, or it could be made of glass material. So these are different types of material as well, very similar to the cell phone. So what are the different types of materials that we can find in nature in general and we supposed to use as engineer? So that's why the study of material, by the way, it is two sides. We do have two perspectives of studying materials. We do have material from the science point of view, and we do have material from the engineering point of view. As we discussed before, the difference between scientist and engineer, or science and engineering. In science, we are interested, or in material science, we are interested to know more about this material in terms of their chemistry, in terms of their microstructure, in terms of their composition, how they are made, what are the properties of this material, and how they could be related to their structure, to their making, to their composition. This is material science, but material engineering, it is another perspective. It is another angle of the material that we should know everything about this material. Then we're gonna know how we can use this material for different engineering applications. So the application side of material, this is known as material engineering. So our objective as engineer, we are the guys who are responsible for identifying the applicability of every single material that we found in nature or we drive or we can make. So our perspective or our objective as engineer is to know how we can make this material, what are the properties of this material, how we can use them in different applications that depend on our measure. So for example, you are as mechanical engineer, what are the most common material that you're gonna deal with or you gonna use for your design or your application? This is something that you should study and know. So that's why one of the courses that you are going to study here in your major, whatever your major is, mechanical or industrial engineering, is material science. Material science, it means that we're gonna focus over the composition, over the science side of this material. Why should I study the material science, not material engineering? In some other universities, they offer material engineering. Some other program, they could offer material engineering. But in the material science course, you're going to focus on the science side of the material. But in the other courses, you're going to consider the application side, the engineering side of the material in the other courses, depending on your major. So your study plan is planned already to cover the two perspectives of the material science. All right, so what are the types of materials? So this is something that we should start with since we are going to talk about materials. Materials, as I mentioned, there are lots of material that we are dealing with every day, and this material could be grouped in general as natural material. Natural material is the material that we drive by nature, that we have nothing to do about this material, we just found them. We can dig into the ground and we can extract these metals or ceramic or polymers. It means that these are natural material that we can drive them from nature. This is one group. And there are some other man-made material. Man-made material, it means these are the material that we can make, that we can develop over the material that already found in nature. So we can generally group metals into two main groups. One metal or one group are classified as natural material, like metals, ceramics, and polymers. So these three types of materials, they are natural material. What does it mean, natural material? Again, it means that we can drive them by nature. We're gonna find them. We have nothing to do about them. But composite, for example, in addition to other types like advanced, we can add to this list so many other materials. Like we can add here advanced material. Advanced material like, for example, nanomaterials and metamaterials and so on. So all of these materials are man-made material. These are things that we are developed, that we are making as whatever scientists or engineers. So these are man-made material. This is the second group. So this is the different types of material that we are dealing with as scientists or as engineers. Metals, ceramics, polymer, these are natural material. Composites and others like advanced materials, semiconductors and so on. So all of these materials are man-made material that we are making them. Okay. So if we're gonna talk about composite, this is a very common type, the most man-made type material that is known these days, and it is already implemented in so many applications, is composite material. What is the concept of the composite material? Is that we are mixing ceramic with metal to end up with another material, with a new form of the material, with some property that is not found in the ceramic by itself or the metal by itself. So like mixing ceramic with metal, this is gonna give a man-made material known as composite material. Also, we can mix ceramic with polymer to end up with another composite material, metal with polymer to end up with another composite material, or we can mix the three together. So mixing these natural material together in one material that is already manufactured, that is already made, we are making this material. This is the concept of the composite material. So what we are going to do now, we're just gonna discuss these different types of materials. We're gonna compare between them in terms of their chemical composition, in terms of their properties, in terms of their application. But the focus is gonna be over these four types. We weren't gonna discuss any advanced material, but as I said, These advanced material and more other material that can be added to this list, these are man-made material. But the natural material, they are metal, ceramic, polymers. Composites and others, they are man-made materials. So for the man-made material, we're going to consider only one example, which is as based on the requirement of this course, sticking to what is already shown in the textbook. It is already composite material that we're going to consider as an example of man-made material. So starting with metals. We should, for every one of these materials, we should know the composition, whatever it is, chemical or non-chemical composition of these materials, and what are their common properties that distinguish them from the other material category or material type. Also mention or know some of the application or some material examples of these materials. Like starting with the metal, what is the chemical composition of metal? A metal material is composed, this is the chemical composition here, of one or more metallic elements. If you remember or you recall from the high school, or even if you already taken the physics class, elements that found in nature can be grouped into either metals or non-metal. These are the elements that are arranged over the periodic table. Like if we're going to talk about aluminum, copper, magnesium, zinc, all of these are metals. But if we're going to talk about oxygen, hydrogen, carbon, these are non-metals. So generally speaking, we can group the element that found in nature into two groups, either metal or non-metal elements. So a metal material is the one that is made only from metal elements. Whatever it is made of one single metal element or multiple metal elements that are chemically joined together. So there should be chemical reaction or combination or mixture between them. It should be through chemistry. So like mixing aluminum with copper to make a material. This material will be classified as metal material. Why? Because it is mainly made of one or more metallic elements only. Here we are talking about the pure metal that is already made of metal elements only. These metals, they do have some common properties that found in all metals. So that's why they are grouped together in one category, in one classification of material as metal. Or in other words, what are the properties which are common between all metals? These are the properties. They are sharing the same properties. They are sharing the same common properties like excellent electrical conductor. So since we are talking about metals, something that you should understand about metal, that they are excellent electrical conductors. So that's why, for example, all electrical wires are made of copper or aluminum. These are the most electrical conductors, metal material. But in addition to these, any other metal material is a very excellent conductor. If we're going to talk about the iron or zinc or magnesium, any metallic material, it is a good conductor for electricity. So that's why it is used in all electronic application. We mainly depend on metals. Why? Their electrical conductivity, it is excellent. In comparison to plastic material, they are insulators in terms of electricity. They don't conduct any electricity. So that's why plastic, it will be classified into another group as polymer, right? Rubber, the same thing, are polymer. They won't gonna be classified as metal. Why? Because they do have different properties than metal. Metal, they are known to be excellent electrical conductor, as I said, like copper. This is a typical example, and aluminum, for example. Also, they are excellent heat conductor. All metals, they are excellent in terms of heat conductivity. They can allow for the heating to or the heat to go through the material itself. And that's why all boilers are made of metal material, whatever the type of this metal material, aluminum or copper or any other nickel or any other metallic material. They also strong material, reliable material in terms of the engineering application. They are kind of strong in comparison to wood, in comparison to plastic material, in comparison to rubber material. So they kind of strong and reliable, and we can use them in so many engineering applications. So that's why one of the essential material that we are using as engineer, whatever your major is, whatever it is, mechanical engineering, civil engineering, industrial engineering, even electrical engineering, we mainly depend on metals. Metals, it is a big deal for us as engineering. Also, in the meanwhile, they are ductile. So what does it mean, a ductile material, which is related to something, a term is known as ductility. Ductility or ductile material, it means that the material has the ability too easy to be deformed without fraction. It could be deformed simply, easily with no fraction. To understand the ductility, let us assume that I'm giving you a stick. Let us assume that you have a stick that is made of aluminum, small stick, like this pen, for example, that is already made of aluminum. This is one option. The other option is that it is made of aluminum. The other option that I'm gonna give you the typical same size and shape of the stick, but it is made of glass. Then I'm gonna ask you to bend it. The aluminum is going to be bended with no problem, with no fracture. Even you can straighten it back again, right? Like you can bend it and you can straighten this stick of the aluminum one more time. It will not be fractured. It will not be cut. It will not be broken. Nothing wrong was gonna happen with this aluminum. Even you can keep on bending it multiple times till it will be cut. It means that it won't gonna be cut from only one or two bends. It requires like so many bends to keep, so it will be heated at the bending area to be cut. So this indicates that this aluminum, it is a ductile material. This, what does it mean, ductility? It is something that can be easily deformed with no fracture, with no, it won't gonna be broken down. But if you try to do the same thing for the piece of glass or the rod of glass that I give you? No. If you try to bend it, it will be completely fractured. So the glass, it is counted or considered as brittle material, is known as brittle material, but the aluminum, it is ductile material. Aluminum, it can be easily deformed with no fracture. It won't gonna break down. But the glass, if you try to deform it, it means that to change the shape. If you try to bend it, like bending this rod that is made of glass, it will be directly fractured as you try or attempt to do so. It means that the glass has zero ductility, and the material with zero ductility is classified as brittle material. So you should understand the difference between these two terms. What does it mean, ductile material? What does it mean, brittle material? Even you could understand ductility like it is flexibility, like flexible material, like rubber, plastic, the kind of ductile material, the kind of flexible material. But flexibility, it is kind of slightly different than ductility, but they are very similar. So you can easily, just to understand what does it mean ductility, think of the flexibility, that this material is flexible. It can be easily deformed, twisted, and so on with no fracture. This indicates that this is a ductile material. But if the material, if you try to bend it, like this bend is counted as brittle material. Why? Because if I try to bend it, it won't gonna be bended. It will be broken down. So that's why it will be classified as a brittle material. All metals in general, some of the common properties of metal, they are ductile. They are very ductile material. As I said, like copper, aluminum, steel, they are very ductile material. You can easily bend them with no problem, right? Also, they has high density. The density is a physical property that they do have a high density, which is related to the weight. It means that they are indicating that they are kind of heavy material. And this makes sense. If you're gonna compare the weight of a piece of copper or aluminum or steel in comparison to the weight of the same shape and size of a piece of plastic or rubber, definitely the metal material is more heavy than the other plastic or polymer material. So plastic, rubbers, they are classified as polymer material. The properties of metal are much more enhanced by alloying. Since we are talking about metal, so these are the properties of metals in general as pure metal. We said that metals in general, they are only made of metallic elements. There is no non-metal elements. We said that in the periodic table, we do have metal and non-metal. Since we are talking about the metals, we should talk about alloying. Something that also you should understand about metal is that the pure metal by itself, it is kind of weak. It is not that strong and reliable to be used in engineering application. In the engineering application, for example, and this what distinguish, a typical example of this is the difference between steel and iron. Many of people, they are mixing between them. Steel is slightly different than iron. Iron is Fe. This is the element. Iron is only made of Fe, but the steel, it is Fe plus carbon. Mixing chemical composition between iron and carbon, this is gonna give us the steel. So the steel, it is a metal alloy, but the iron, it is a pure metal. Iron by itself, it is a very weak material. It is not reliable in terms of engineering application. But in order to enhance the properties of the iron, which we know exactly that it is weak, it is not reliable, and so on. So one of the things to enhance its properties, we found as material scientists or material engineers even, we found that if we added a very small amount of carbon to the iron, this is gonna end up with an alloy. This alloy is with much more enhanced properties over the pure iron itself. So the pure iron, which is just Fe with no any other elements, it is very weak, it is kind of weak, it is not reliable, it is not good in terms of so many engineering application. But in order to add value or enhance the properties of the iron, which is weak, if we added a very small amount of carbon to it, we are going to much way enhance the properties of this iron, and in that case we're gonna end up with alloy. So mixing iron, which is metal, the iron it is metal, the carbon it is non-metal, so the carbon it is non-metal, and the iron itself it is metal. So mixing the metal element with a very small fraction or amount of non-metal element, this adds more value and enhances the properties of the material. And this process, adding the non-metal to the metal, is known as alloying. So this process is known as alloying, and this is a huge industry for any country. Any country, they do have their own alloy, they do have their own industry for steel making, for example, which is depend on the alloying concept. So what does it mean alloying? It means that we are adding a small fraction of the non-metal to the metal element with the aim to enhance its properties. So the properties of the metal are much way enhanced by alloying. What does it mean alloying? Is the process of adding a very small amount or fraction of non-metallic elements to the pure metal. We said that the pure metal is only made of metals. But if we added non-metal element with a small fraction to it, we are going to enhance its properties. A typical example is steel and iron. Iron itself, which is pure Fe element, it is kind of weak material, not reliable. When we add carbon with an amount as small as 0.1% up to 2%. In some cases, we can even add 0.05 or 0.02%. Very small amount of carbon. Like, for example, you do have a plate of food and you're just gonna add some salt to it. So the salt, it is like you're gonna add to the steel or to the iron, you're gonna add a very small amount of carbon. This is gonna give more price, more value to the iron itself. It becomes a steel. So something that you should understand, that the steel, it is a metal alloy, but the iron, it is a pure metal. Steel is a metal alloy, which is a very strong material in comparison to the iron. So all the iron we are not using as engineers, civil engineers, mechanical engineers, industrial engineers, we are not using iron as iron by itself as pure. And instead we are using iron as a steel, which is the metal alloy. Make sense? So this is typically the difference between an alloy and a pure metal. Materials here is ceramics. So ceramics is different than metal. In terms of the chemical composition, yes, they are different. Ceramic materials are, or a ceramic material is a compound. So it is compound here, it means that it is a chemical compound between two different elements. So this is something that you should study in the physics class. When we talk about a chemical compound, this indicates that it should be made of two different elements, not the same type. But here, for example, metals are composed of one element type, which is one or more metallic elements. But here, it is a chemical compound that is made of metal and non-metal elements. Metal plus non-metal. We said that elements in the periodic table would have metal, we do have non-metal. If we're gonna take one metal and one non-metal element and we are going to mix them together chemically, this is gonna end up with a chemical compound. This chemical compound gives a ceramic material. But this could be kind of confusing. Why? Because if we are going to mix metal with non-metal, We have done this through the alloy. In alloying, we are adding metal to non-metal. Or we are adding, to be more accurate, we are adding non-metal to the metal. So if the alloy can be counted as ceramic material, no. The alloy is still counted as metal. Why? Because the fraction or the amount of the non-metal that we are adding to the metal, it is very negligible, very small. It is 0.1 up to 2% at maximum in so many applications, in so many of the alloying process. It means that the fraction of the non-metal, it is negligible, and we adding it just to enhance the properties of the material. As I said, like the typical example, for example, if you are eating a dish of any food type, adding the salt to the food, it won't gonna change the type of the plate itself. The same thing here for alloying. In alloying, we are not changing the metal to be metal. It is still metal. We're just adding a very small fractional amount or adding a salt over metal. It is still anyway metal. But the ceramic, it is made of metal and non-metal, but the fraction or the amount of the non-metal, it is high in comparison to the case of the alloy. It is very high fraction or amount of non-metal that is going to be mixed. In some cases, the non-metal, it could be even higher than the metal material to end up with the ceramic material. So the ceramic, it is a chemical composition of or compound of metal and non-metal, and they most frequently depend on oxides, nitrides, and carbides. It means that these are the non-metal. Carbides, nitride, oxides, these are non-metal. So these are the most three groups of non-metals that could be used for making ceramic material. What makes ceramic different than metal is their properties. There is common properties among all the ceramic material that they are excellent electrical insulators. If you're gonna compare metals, they are excellent electrical conductors, but insulators on the other side, they are excellent electrical insulator. Like for example, so in that case, if you're gonna have any material that is excellent electrical insulator, which would seem like it is metal, because the category or the shape, even the sense of the ceramic material, when it is compared to metal, they are very similar in shape and everything. Okay, in many of the ceramic material, in comparison to the metal material, they are very similar. But there are some other ceramic material which are totally different. Like for example, the glass. Glass, it is a ceramic material. Glass, it is not conductor to the electricity, right? But as I mentioned, there are some other, like carbides, for example, in the shape of the carbides and the ceramic material and the metal, they are very similar in terms of the shape. But they are totally different in terms of properties. So that's why carbides will be classified as ceramic, but metals are just metal. Why? Carbides, they are not good conductors in terms of electricity or even heat in comparison to the metal. So that's why as a common property of ceramic material, they are excellent electrical insulator, they are excellent heat insulator. As you can see, it is the opposite, the totally opposite to the metal. They are relatively strong. They are much way stronger. Many of the ceramic material, they are much way stronger than metals. Carbides are much way stronger than the metal material. But in the meanwhile, they are very brittle material. We said that a typical example, the glass, it is a brittle material, but aluminum, it is a ductile. So aluminum, it is metal, glass, it is a ceramic material. A typical example of a brittle material that is made of ceramic is the glass itself. So the glass, it is a very brittle material, and definitely it is a ceramic material. Also, they do have high density, even higher than some of the elements of or materials or ceramic material. They do have higher density. It means that they are more heavy in terms of the weight than the metal material itself. But as I mentioned, so many types of the ceramic material, they are much more stronger than the material, than the metal material. In addition, they are good, excellent insulators. So for example, if we are making we are using metals and ceramic in making boilers. Because the boiler itself, especially if we're going to talk about at very heating, like melting metal, like in furnace that use for melting metals, they are mainly depend on ceramic. They are made like, there is a brake type that is already made of ceramic material that is not conducting heat. Okay, so it is a very excellent insulator in terms of heat, and in that case we can use it for melting metal. So for example, the industry for steel making, completely it depend on the ceramic material for the like to cover the interior of the furnace that allow for melting the metal inside it. Okay, so examples of ceramic materials include glass, alumina, which is Al2O3. So it is aluminum and oxygen. So the aluminum and oxygen, aluminum it is metal. The oxygen it is non-metal. Non-metal. So we are mixing aluminum with a non-metal like oxygen. This is gonna give us the aluminum oxide, which is commonly known as alumina. This alumina is one of the strongest material. It is a very strong material, even it is stronger than so many of the metallic material. Titanium carbide also is an example, like titanium and carbon. And carbon also silicon carbide, silicon and carbon. So the silicon it is a metal material, carbon it is non-metal, and we gonna end up with this ceramic material. Alright, so the third group here of material is polymers. So here we're still talking about the natural material. Polymers are organic materials that are mainly formed of carbon and hydrogen. They depend a lot over carbon and hydrogen, and remember, carbon and hydrogen, these are non-metals. So they are mainly depend on the non-metal, especially the carbon and hydrogen, in addition to the other elements definitely could be used. Polymers include the familiar plastic and rubber material. Like all the plastic, they are polymers, or rubber materials, they are polymers. And polymers in general, they can be classified into three categories. We do have thermoplastics or thermoplastic polymers. We do have thermosettings polymers. We do have elastomer like rubbers. These three types, so polymers, it is not just one type of polymer. No, we do have so many, bunch of types of polymers, plastic, but just to understand what are these polymer material, think of the plastic, any plastic material it is polymer, any rubber material it is polymer material. Okay, they can be grouped into thermoplastic polymer, thermosetting polymers, and elastomers, which elastomer like the rubber material or rubbers. These three categories of the polymer, they are different in the properties. But as you can see, as we discussed in metals or even ceramic, there are some of the common properties, like all the ceramic, they almost sharing the same properties, all the metal, they almost sharing the same properties. But polymers, some of them, they do have certain properties, some other, they do have different properties. So that's why we do have a classification of the polymer as thermoplastics, thermosettings, and elastomers, right? They are different in terms of the properties. I won't gonna explain this because this is not the objective of this part, because there are lots of details, because they are different in terms of the structure of the polymer material, in terms of the properties. For example, I'm just gonna give you an example. There are some of the types of polymer material, like plastic, for example. When you heating the plastic, it will be shrink. Some other, it will be melted, like it's going to behave like a metal. So it means that they are already exhibiting, or they already do have different properties that make one polymer is different than the other one. Make sense? So that's why we do have three groups or three types of polymers. Something that you should know, just these three categories. But the details of the properties, what distinguish plastic, thermoplastics from thermosettings from elastomers, this requires lots of detail, and this definitely will be covered in the material science class. But there are some common properties in all of these groups. So there are, as I said, there are some common properties, and there are some other properties which make them, the thermoplastic is different than the thermosettings, different than the elastomers. The common properties that they are excellent electrical insulators. All of them, they are excellent insulators. All of them, they are excellent heat insulators, like the ceramic material. But the ceramic material, definitely, it is more heat insulation. It is more electrical insulator, or I'm sorry, the polymers like rubber, plastic, and so on, they are excellent electrical insulator, even more than the ceramic material. Make sense? But ceramic material, they are more heat insulators than the polymer material, since they are more strong. But they are relatively weak. This is some of the drawbacks of this polymer. They are relatively weak. So we are not involving them. These days, there is in the industry and the engineering application, we are depending a lot over these polymer. Like you could say that this plastic material and polymer, they are involved in so many things that you are using every day. Like for example, the body of your computer is already made of rubber. If you're gonna talk about the car, the interiors of your car, it is 90% made of rubber materials. So it is used a lot, but in application that doesn't require a heavy load or ability to support forces or a strong material like metal or ceramic. So we're just keeping the use of metal and ceramic in the situation or the application that require a very high force or a strong material. In that case, we have to use either ceramic material or a metal material. But polymer, they are weak. So we are using them just for the decoration, for the exterior of things that basically won't gonna subject or carry any heavy forces or loads. In that case, we can use the polymer material. In the meanwhile, they are very ductile, many types of them, like rubbers, elastomer, they are very ductile, easy to deform. Plastic, some of them are very ductile, but there are some types of the plastic that they are brittle. So that's why we do have different categories of polymers. Very low density, they are very light material, and this is the good thing of polymer, that they are very light material. So that's why we are involving them a lot in so many applications and so many devices that we basically use. So it would be easy, or it would be light in terms of weight in our hand. Like the cell phone, it depends a lot over polymers and plastic material. Why? To make it more light in your hand, and instead of using depending only over ceramic or metal material, it will be much more heavy. Examples of polymers include all plastics, nylon, rubber, and so on. So these all are the different types of polymer. So as we discussed here, these are the three types of natural material. These are what we drive by nature. We have nothing to do about this material. These are the natural material, but we can make composites. Composites is a typical example of a man-made material. This is the thing that we can make. A composite material is a composition of two or more different materials. Two or more different materials, not elements. So what does it mean this? It means here in composite, and this is something that you should understand, that there is no chemical composition. But alloying, for example, there is a chemical composition that is required. For example, in alloying, we are mixing element in metal. It is made of one or more metallic elements. In ceramic or alloy, we are adding non-metal element, non-metal material. Material, it means that it is already material that there is no ability to do any chemical reaction anymore. There is no chemical composition anymore because it became a material. But an element, it means that it could be used for making a material through a chemical reaction. It means that in alloying, we are doing a chemical reaction between metal and non-metal. The same thing for ceramic. We are doing a chemical reaction between metal and non-metal. In polymer, we are doing a chemical reaction between carbon and hydrogen and other metal and non-metal materials. But in composite, there is no chemical reaction here. There is no chemical composition. It is a mixture. So we're going to say that, to be more accurate, a composite material, it is a mixture. We can say that it is a mixture. Mixture indicates that there is no chemical reaction, just mixing two materials together, and you can clearly see the difference between these two different components. One or more different materials. They should be different materials. Like for example, mixing metal with non-metal. Material with ceramic. Mixing metal with polymer. Mixing metal with, ceramic with polymer. Mixing the three together to form a composite material. This is going to be the concept of the composite material. The constituents of a composite material are natural material like metal, ceramic, or polymer. We can mix any two or the three together to end up with a composite material. While we are making composite material, composites are made with the aim to obtain enhanced properties. The same concept like alloying. But in alloying, we should involve some chemical reaction. By enhancing, in order to enhance, we said that pure metal by itself, it is kind of weak, it is not reliable. To enhance its properties, add some non-metals chemically through a chemical reaction. But here, the same concept for composite, we said that as we discussed, metals, they do have their own specification. They do have their own good and bad properties. Ceramic, they do have their own good and bad properties. Polymer, they do have their good and bad properties. So how about if we can mix This is the basic idea behind the composite material. How about if we can mix metals with ceramic? So we're gonna get the good of the metals and the good of the ceramic to end up with a better material, which is much more, way better than the constituent material. So the metal is one constituent, the ceramic is another constituent material. So when we mix them together, we end up with a composite, a new material that is with a better enhanced properties over the two constituents, the metal or the ceramic. The same thing if we mix metal with polymer, ceramic with polymer material, for example. So the objective is made with the aim to obtain enhanced properties which cannot be obtained by either one of the material constituents. Metal itself doesn't have the properties that we can drive or we can obtain by mixing metal with ceramic. Ceramic by itself has no properties, doesn't have the properties that we can obtain by mixing ceramic with metal, and so on. Common properties of polymer this should be composite material. Common properties of composites include good electrical insulators, good heat insulators, strong, ductile, low density, and so on. So one of the low density, it is one of the excellent thing of using composite material in the aeroplane application. For example, the weight. For an aeroplane, it is a big deal. So that's why, for example, when you travel from one country to the other, there is a limit over the weight of your luggage. Why you are putting this limit, and if you exceed the limit, you're gonna pay cash for it? Because the way in the air up there, it is a big deal. Because this airplane, it has a limit over the weight, so the thrust, and it could be able to fly in the sky, in that case. Make sense? So that's why we are in the industry or the making of the airplane. The body of the airplane mainly depends on very light material. We try to use very light material as much as we can, but in the meanwhile, this material should be strong. One of the lightest material ever is magnesium. The next one is aluminum. Aluminum is a very light material, has very low density. So that's why, for example, the body of the airplane, it is made of aluminum. But if we depended only over aluminum, it's gonna be very weak material. Aluminum, it is very light, has low density, so it is good to make the body of the airplane made of aluminum. But aluminum by itself, it is weak in the meanwhile. It won't gonna able to support the thrust and the hitting of the birds or the hitting of the air to the body of the airplane. It will be damaging. So how we can fix them? We found that, how about if we're gonna make it composite? How about if we are going to enforce, to strengthen the aluminum by adding some small particles inside the aluminum to give it more strength, to make it more stronger, to support the body of the airplane itself while it travels over there, to support the hitting of the air or the thrust of the air against the drag of the air against the airplane itself. So that's why composites are made. This is the composite. So composite, one of the typical example of this composite that used for the airplane, that we bring like a sheet, think of it like in this way. This is the aluminum, which is very pure aluminum material, and we just embedding inside it very small tiny particles. We could make it like nanoparticle, nano size, very thin that it can be seen by the naked eye, very small thing. And we distribute these particles inside the aluminum sheet. In that case, this is gonna give much more strength to the aluminum and makes the aluminum more stronger than it being just pure aluminum. This is the basic idea of the composite material. We still, after we do this mixture, after we make this material, we still can distinguish the aluminum from the other particles. So these particles, it could be made from a stronger material like ceramic material. For example, it could be made of ceramics. We said that, as we agreed, ceramic are much more stronger than metals. Aluminum, it is a metal material. So here we are mixing metal with ceramic. Mixing metal material with a ceramic material to end up with a composite. But after we mix them together, we still can distinguish. If we broke the material and we're gonna look inside the plate, we can easily see the particles of the ceramic separate from the aluminum, or we can distinguish the two materials still inside when we look inside the plate itself. This indicates that there is no chemical reaction here. They are still separate, but they are mixed together to form one material which more stronger. In the meanwhile, it is very light density because we just added a very small. The ceramic, it is heavy. So if we decided to make the entire plate of aluminum, we said that aluminum, it is light, it is good thing, but it is weak. But if the other option is that to make the plates entirely from ceramic, it is very strong. This is gonna give a very strong body of the airplane, but the problem is that it's gonna be very heavy. So the airplane, it won't gonna able to fly. How about if we can mix? How about if we're gonna add very small fractional amount of the ceramic that with the aim to enhance the strength of this aluminum, so we still have a lightweight because this fraction of the ceramic is very negligible, so nothing will be changed significantly in terms of the density. We still have low density, but in the meanwhile it is strong. And this is the good thing of the composite material, and this is the basic idea of making the composite material. Make sense? So that's it for the material side. These are the different types of material. The objective again is just to discuss to understand that we do have three natural material and we do have man-made material. A typical example of the man-made material is composites. Also to know the difference between them in terms of the chemical composition, in terms of the properties, in terms of the examples or the application between metal, ceramics and polymers, and understand the concept of behind the composite material. Make sense? Alright, so one of the things that we are going to discuss here, just to finish the mechanical design part, is the factor of safety. What does it mean, a factor of safety? Factor of safety, if you are, as we discussed, and during the engineering design process, there is one of the steps which is the problem definition, and within the problem definition is just to know the objectives and build the design specification. Like there is some specification, there are some of the constraints that we have to stick with in order to end up with a successful design. Or whatever the thing that you are going to design, it could be something related to civil engineering, related to the mechanical engineer, like design a machine or a mechanical component. Even if you are going to design a process, if you are going to design a procedure as an industrial engineer. So the thing that you are going to design, you should count for some of the safety or consider some factors into account while you already doing the design, like the factor of safety, for example. One of the things, for example, is the foolproofing. I'm just going to give you a typical example of the foolproofing. If we're going to consider this calculator and the cover. So this calculator and the cover, they already designed in such a way that the calculator can be closed with the cover in one direction, in one setup. Like for example, if I decided to turn the calculator in this way and try to fix it into the cover, it won't gonna work. Why? There are lots of things inside here that already made these guys, these engineers who designed this calculator, this body and this thing. We are not talking about the electronic things and the calculator, forgot about. I'm talking about the design of the cover and how it is mounted and fixed with the calculator. So this thing is already designed to give the fixation of or mounting or closing the calculator or covering the calculator in one specific direction. So there are some bends and some features already added here to prevent fixing the calculator in a wrong direction. This is known as foolproofing. This is one of the factors. This is one of the things that you should consider when you design for anything, whatever it is. Like for example, since we are talking about mechanical engineering, in mechanical engineering, the factor of safety is a big deal. The factor of safety is one of the important factors that we should consider. So in terms of mechanical engineering, what does it mean, a factor of safety? The factor of safety, it is simply the strength divided by the maximum stress. As we discussed over the previous slides, over the previous videos, we said that the material, because of the force acting on the material, it will be subjected to some stresses. And we said that the strength, it is one of the properties, which is the yield strength of the material. It is one of the properties of the material. So any material that we are going to use for the design of a gear, for the design of a shaft, for the design of any mechanical component, this material has a specification, has some of the properties. It could be composite, it could be polymer, it could be ceramic, it could be metal. So the question is, if I am interested in making a shaft that is going to be used in a machine, what is the suitable material that from which I should make this shaft? Can I make it from metal? Can I make it from ceramic? Can I make it from polymers? This depends on the specification, depends on the design specification that we are going to define when we started the design process, based on a factor of safety. So the factor of safety relates the strength of the material that you are planning to use to the maximum stress that you need. This shaft, when it is used into the machine, it will be subject to stresses. There should be forces, and these forces can be converted into stress. So in case that we do have the stress that acts over the shaft is higher than the strength of the shaft, definitely the shaft will be broken. It will fracture. The design, it will fail. So if the factor, it means that if the maximum stress acting over the shaft, it is bigger than the strength, this is gonna give you the factor of safety less than 1. If it is less than 1, failure will happen. Bad design, not good design. So this is something that you should consider when you do the design calculation before you bring this design into reality, or you do or manufacture your design. You have to make sure of the factor of safety. You have to make sure that the factor of safety is bigger than 1. What does it mean factor of safety is bigger than 1? This indicates that the strength of the material, it is bigger than the stress that acting over the material. That the material is stronger, that the material is strong enough to support these forces that is going to generate once you implement the shaft inside the machine. Once you do so, there are some forces that is going to generate, there are some stresses that is going to generate. This stresses should be lower than the strength of the material, keeping the material to be working in the elastic region. If you remember over the stress strain curve, as we discussed the last video, we do have within the elastic region, we do have, this is the yield, then we are going to the plastic, right? So this yield point, the value of the stress that is correspond to this yield is known as the yield strength. This is the yield strength of the material. This is the measure of how the strong or the ability of the material to support stress. This is the maximum stress that the material can withstand without yielding, without going to the plastic deformation. So our objective as design engineer, mechanical design engineer, is to keep using the material at stress levels lower than the yield strengths. All the time, the maximum stress that should be acting over the shaft or over the mechanical component, it should be lower than the strength of the material. Other than that, we are going to end up with a bad design. So this is what does it mean a factor of safety. So the factor of safety is the ability of a mechanical element or a mechanical component that is something related to the mechanical design to be viable or reliable beyond its expected or actual load value. How can we use it or not? So this is the factor of safety. It is the ratio of the strength of the mechanical element material, the strength of the material, it depends on the material. So that's why we had to cover the different materials to be applied to the maximum stress acting on it. This is gonna give us the factor of safety as a strength divided by the maximum stress. As we said, in case that it is bigger than 1, bigger or equals, this is the minimum thing, it should be equal. But even we should consider more than 1, it means that we're gonna have a good design. So your objective as a mechanical design engineer, when you design any mechanical component, you have to make sure that this factor of safety is bigger than 1. If it is less than 1, don't do it. You have to change your design. Definitely without manufacturing and making the machine, if you try to do so, you're gonna end up with a bad design, and definitely your machine it won't gonna work. Make sense? This what does it mean, the factor of safety. Also, something else that we should consider when we do design for any mechanical component is the dynamic effect. What is a dynamic effect? This factor of safety here, it is the simplest factor of safety or the simplest criteria that depend on the static load. We said that, or as we discussed, load or a force. The force it produces stress. But the force itself, it could be static or dynamic. What does it mean this? Static force, for example, if I'm going to apply push against the table. So this is an static force. Why? Because the force has been applied steadily and the force is fixed over time. It is not changing. So this indicates that this is a type of a static force. So the force is not, if the force is not changing over time, or if the force direction or magnitude is not changing over time, this indicates a static force. As we discussed before, the force, it is a vector quantity. What does it mean, vector quantity? It means that it requires magnitude and direction, right? So in case that we have a force, let us consider these two scenarios. Assume that you have a shaft that is supported by two bearings. We said that shaft should be supported by two bearings before, right? And this shaft is subjected to a force F. But this force is not changing. What does it mean? Or the shaft is stationary. The shaft is not rotating, non-rotating shaft. So a non-rotating shaft, it will be counted as axial, right? We said that the axis, what distinguishes axial from a shaft is that the axle is not rotating, but the shaft is the thing that is rotates. So the axle, when it is subjected to a force, this force, it will be considered as a static case. Why? The axle is not rotating, is not moving. Static, it means that an object that is not moving, as we covered before when we were discussing the force. So this force is fixed, is constant. In terms of magnitude, the value of the force is still the same. The direction of the force all the time directed down. And the axle itself is not rotating. So in that case, this is a static load. So we're going to count this case as a static load condition. The other scenario is, how about if we do have the same design, the same thing, but it is like a shaft. A shaft, it means that it will going to keep on rotating. So we do have here some bearings in that case, and this is going to work as a shaft. So in this case, we do have a rotating shaft. And we're going to have a force acting on it. Even if the force, it is stationary, it means that the force is static. What does it mean, the force? The direction of the force is the same, the magnitude of the force is the same, but because of the shaft being rotating, there is a dynamic load. It means that this shaft is going to work like we are bending the shaft in this direction and bend on the opposite direction. So it means that the direction of the force, it is assume like you have the force, like the direction of the force can be swapped, like we can push in this direction and then we're gonna push in the opposite direction. Even we can change the magnitude, the value of the force. We can push with 10 Newton, then we're gonna push in this direction with 20 Newton, then we're gonna keep on repeating the process, push in this direction and push in the opposite direction. So this is known as dynamic load. It means that the load changes over time in the value and the magnitude. In addition, you do have the shaft is already rotating. Another thing that you should understand about this shaft or the dynamic effect, that it adds more force over the shaft because of the rotation of the shaft. So in the static case, we do have the force is not changing in time, over time. Whatever in terms of magnitude or direction of the force is still the same. In the meanwhile, the mechanical component that we are doing design for is stationary, is not moving. It is static, like the case of non-rotating axle. So this problem will be counted as a static load condition. We are going to do the design based on the static load condition. The other scenario is that you do have either the component itself is moving, like the case of rotating shaft, it already moves. So there is a dynamic effect here. There is another dynamic effect that the force itself, it could be changing. The force, it could be dynamic. The force, it could be changing in terms of the magnitude and the direction. So these are two dynamic effects here. You got my point? So we do have the option is that you do have only the shaft just rotating and it's still the force is still the same. Or we do have the force is it changing over time and in terms of magnitude and direction, in the meanwhile the shaft is rotating. So we do have two dynamic effects in that case, right? Both they do produce some extra stresses, some extra forces over the static case. So if I have done my calculations, if I've done my design based assuming that I do have a static only, while the actual case that the shaft should be working dynamic routine, in that case definitely your design is bad design. It is not a good design. Definitely the shaft will be broken. Why? Because you didn't consider the dynamic effect. Why? Because the dynamic effects adds more force, adds more stresses, which is not seen but it is hidden because of being dynamic. One of these extra forces is the inertia. Inertia, this is like, for example, if we can apply the Newton's second law that states that the sum of forces, it should equal to zero in case that we are working static. So for the case of non-rotating shaft or non-rotating axle, in that case, the sum of the forces acting of this axle, it should be zero. And since we're already working as a static, but under the dynamic effect, the sum of the forces will not be zero. There will be an extra force. This is the inertia that already is going to equal to the mass times the acceleration, the mass of the shaft times the acceleration of this shaft, because it is rotating, it is dynamic, it moves. So because of the movement of this mechanical component, there is an inertia that is going to be generated because of the movement of this mechanical component. So this is the inertia. This is an excess energy, an extra force that we have to consider. And this extra force definitely it will produce more stress. So if we're gonna go back here to the factor of safety, and the actual problem that we're gonna deal with is dynamic. And for some reason, we assume that it is static. So in that case, we are required to calculate the maximum stress that acting over the material. So we calculated this maximum stress based assuming that it is static. So we're gonna end up with a factor of safety that is bigger than 1. It is good design based on the calculation. But once we fix this shaft into the machine, it had been broken quickly. Why? Because of our design, we didn't consider the dynamic effect. Because why? Because if you consider the dynamic effect, this adds more stress that is hidden, not seen to us, but we have to consider that comes because of the dynamic effect. We should have considered it when we did design. In that case, if we consider it, we're gonna find that the factor of safety will be less than 1. It means that our design is already bad. Why? Because we didn't consider the dynamic effect. So the dynamic effect here is a big deal when it comes to the design of mechanical elements. And why the dynamic effect is big deal for us as mechanical design? Since we are talking about a mechanical design or a machine, we said that what distinguishes a machine from a structure is that the machine should have mechanism, and this mechanism should be moving. So anyway, there is a dynamic effect is there. So that's why when we do design for any mechanical component, we should consider that it is movable, that is going to move, there is a dynamic load effect that is going to exist here, and we have to consider the extra stresses due to this dynamic effect that is in motion. So when it comes to the design of mechanical element that is in motion in a mechanism of a machine, their dynamic effect is a big deal that it should be considered. These mechanical components should be carefully designed considering their dynamic effects. When a mechanical component moves, there is an extra force and stress that is going to generate because of its inertia. In addition, it is subjected to dynamic loads. The dynamics, so the inertia, as we mentioned, it is the multiplication of the mass times the acceleration, which is going to be like kilograms per meter square or slug per feet square, depending on the unit system. Also, there is a dynamic load. So the dynamic load, there are different types of dynamic load. We don't have impact load, or like these two types of impact forces. So the dynamic load is one of the changes, is the one that it changes its magnitude or direction or both with respect to the time, as we discussed here. So the force, it could be changing in terms of magnitude and direction, or both. Like for example, we could have the same direction of the force, but the force is going to keep on changing over time. It's going to increase from 0 to 10, from 0 to 10, then it's going to decrease back again to 0, then it's going to increase one more time, and so on. So this is not a cyclic increase or a change of the force magnitude over time. So here the magnitude of the force is changing over time. The other option is that we're going to keep the magnitude of the force the same, but the direction of the force is going to alternate, is going to change. Like you're going to have the direction of the force down, then up, down, then up, down, then up. So it is cyclic, repeats over time. This is known as a cyclic load, or that explains the change in the direction that comes because of the change in the direction while the magnitude is still the same. Or we can change both. We can change the magnitude and the direction, both of them at once, when we already doing the design or for the operation, when we're already using this shaft. So a dynamic load is the one that it changes its magnitude or direction or both with respect to the time. This is the, what does it mean, a dynamic load? We do have different types and more than these types even for a dynamic load, but we can consider like the cyclic load or the impact load. The cyclic load, like this one, as you can see, it is something that is gonna keep on repeating, pushing and release, pushing and release, pushing and release over the time. So it is a cyclic load. The cyclic load produces something that we call as a fatigue effect. What does it mean? For example, if I give you a wire, a piece of wire, like a copper wire, electrical wire, and I ask you to cut it by hand. So if you try to pull it, you're gonna hurt yourself. But the other option that you're gonna keep on bending, right? You're gonna keep on bending it till it will be completely fractured. This bending action is known as a cyclic load. What you are doing a cyclic load. You bend in this direction and you switch. Change the magnitude. You're still applying the same bending force, but the direction is cyclic. The direction is repeated, cyclic, over cycle. So this is one cycle, second cycle, third cycle, and so on. So after a certain number of cycles and repeating this action, it will be cut. Why? Because of a fatigue effect. Initially, after the first cycle, it is not broken. It is not cut. Why? Because the fatigue effect is still small and it's gonna keep on fatigue, increasing the stress as you're already doing more cycle. This is gonna result at the end in making this wire, it will be completely cut because of the cyclic effect. So this is another factor that we have to consider. This gives more stresses, more forces over the mechanical component, over the static load that we conventionally could understand. Okay, so that's why, for example, one of the factors that you should consider when you study the mechanical design course is this cyclic load or the fatigue load effect. Another factor is the impact. Impact is hitting thing. Hitting an object, like for example, if I apply my hand, my bare hand over and pressing over the table, this is a static load that is gradually applied and steadily applied over this surface. But hitting over the surface, this is impact. The impact forces will have more effect than the conventional static load. Like this impact, like this shot already going through the wall, because it hits, it has an impact effect and penetrate through the wall. So this is a typical example of an impact load. Like this hammer is going down with a high force and hitting the object at a sudden applied force at a specific instant of time, and this force will be removed. This is known also as an impact load effect. It has an effect that also should be considered when we do design for these mechanical components. So static load is gradually applied and remains static and constant after reaching its maximum load, but the dynamic loads, they are changing over time, magnitude and direction over time, or both, like the case of impact load or cyclic load. So all of these factors and more, even the surface, the wear and other things, definitely we're going to study this with more detail in the mechanical design course. So when generally speaking, this discussion, we can conclude one main thing, is that when you do design, you should account all the aspects that could be significantly impact your design, and you have to collect all of these aspects and consider them when you do the design calculation. If it is only static and you are pretty sure that it is only static, no problem. Go ahead and do the design based on the static load condition. If there is if the mechanical component is going to move, you have to consider the dynamic effect. If you didn't consider it, your design, it will be counted bad design. It is not a good design. If there is an impact load effect, you have to consider the impact effect. If there is a cyclic load effect, you have to consider the fatigue effect. So any factor that is already found in the real example or the real situation of the mechanical component, we have to consider it when we do design for this mechanical component. In addition, we have to consider the material type, the material strengths, and all the stresses that could be acting over the mechanical component. Make sense? So that's it for today. We discussed today lots of things. We discussed the different types of materials. Also, we discussed the factor of safety and other factors that we should consider when we do design for mechanical component like the dynamic load effect. Make sense? So that's it for today, and thank you, and see you in another video.